Here's the thing about Earth. Every 100,000 years, like clockwork, the planet freezes. Ice spreads from the poles, glaciers march across continents, sea levels drop hundreds of feet, entire ecosystems shift toward the equator. Then just as predictably, the ice retreats. The planet warms, life spreads back north and south. This has happened over and over for millions of years. The pattern is so regular, you could almost set your watch by it. Almost. Because here's what makes this truly strange. The cycle isn't quite perfect. It's close, incredibly close. But there are wobbles, variations, times when the ice should have advanced but didn't. Times when it should have retreated but lingered. And nobody knows exactly why. If you're using this to fall asleep, that's exactly why I make these videos. Maybe subscribe and let me know where you're watching from and what time it is. I always check the comments and it's fascinating. We know the ice ages happen. We can measure them in ice cores drilled from Antarctica, in ocean sediments, pulled from the deep sea floor in the rocks, scraped and carved by ancient glaciers. The evidence is everywhere. We even know some of the reasons. Earth's orbit changes shape. The planet wobbles on its axis. The tilt shifts slightly. These changes affect how much sunlight hits different parts of the planet. But there's a problem. Those orbital changes alone aren't enough. The math doesn't quite work. The wobbles in Earth's orbit should create temperature changes of maybe 1 or 2 degrees. Instead, we get ice ages. Full glacial periods where ice sheets cover half of North America, where the climate shifts so dramatically that entire species go extinct, or evolve or migrate thousands of miles. Something is amplifying the signal, taking those small orbital nudges and turning them into massive climate swings. Scientists have been trying to solve this puzzle for over a century. They've proposed dozens of theories, some elegant, some bizarre, some that seem perfect, until new evidence proved them wrong. The answer, it turns out, involves everything. The oceans, the atmosphere, the ice itself, carbon dioxide locked in rocks and released by volcanoes, dust blown from deserts, plankton in the sea, forests spreading and retreating, all of it connected in ways we're still figuring out. And the really unsettling part, we're living in one of the warm periods right now. Between ice ages, the ice will come back, maybe in 10,000 years, maybe in 50,000. This cycle isn't done, unless we've broken it, which is a whole different question. Over the next hour, we're going to walk through 800,000 years. We're going to explore why Earth freezes, why it thaws, and the question that has puzzled scientists for a century: why does the weakest orbital cycle create the strongest effect? Take your time. We have all night. The first person to really understand that ice ages happened wasn't a scientist. He was a Swiss carpenter and hunter named Jean-Pierre Perraudin. The year was 1815. Perraudin spent his days in the Alps guiding travelers through mountain passes. He noticed something strange. Huge boulders sat in the middle of valleys miles from any cliff they could have fallen from. The rocks didn't match the stone around them. They were granite, but the valleys were limestone. Perraudin had a theory. The glaciers had carried them. Imagine standing in one of those valleys. The air is thin and cold. Mountains rise on all sides, their peaks white with snow even in summer. And there in the middle of a grassy meadow sits a boulder the size of a house, smooth on one side as if something had polished it, covered in scratches that all point the same direction. Down from the mountains, you bend down and touch the scratches. They're deep, precise, not random marks from a rock slide. Something dragged this boulder for miles, scraping it against the bedrock below. Perraudin told this to a Swiss engineer named Ignaz Venetz. Venetz laughed. Everyone laughed. Glaciers move slowly, maybe a few feet per year. How could they possibly carry boulders the size of houses across entire valleys? But Perraudin was persistent. He showed Venetz the scratches. Long grooves carved into solid rock, all pointing the same direction, down from the mountains. Venetz started paying attention. He looked at the boulders again. He measured the scratches. He talked to other mountain people. They all said the same thing. The glaciers used to be much bigger. You could see where they'd been. The marks were unmistakable. Venetz became convinced. He presented his findings to the Swiss Society of Natural Sciences in 1821. Most scientists dismissed him. Few listened. One was a young geologist named Louis Agassiz. Agassiz was skeptical at first. He went to the Alps to prove Venetz wrong. He spent the summer of 1836 studying glaciers, measuring them, watching how they moved, looking at the rocks they carried. Picture him there in a valley high in the Alps. He's young, ambitious, certain he's about to debunk a foolish theory. He sets up his equipment. He measures the glacier's edge, drives stakes into the ice to track its movement. Days pass, weeks. The stakes move. Not much. A few inches, a foot, but they move. He examines the rocks at the glacier's base. They're scratched just like the boulders in the valleys below. He traces the scratches back, following them up the mountainside. They go for miles. Continuous grooves in the bedrock, all pointing down from the peaks. He came back convinced that Venice was right, more than right. The glaciers hadn't just been bigger. They'd covered most of Europe, all of Scandinavia, much of Britain, parts of Germany and France and Switzerland. Agassiz called it the Ice Age, Die Eiszeit in German. He presented his theory in 1837. The scientific community was not impressed. The problem was the dominant theory of the time, catastrophism, the idea that Earth's features were shaped by sudden violent events. Most geologists believed in the biblical flood. They thought the boulders had been carried by rushing water. The scratches were from debris in the floodwaters. Everything could be explained by one great deluge. Agassiz was proposing something different. Slow change, gradual processes, ice advancing over thousands of years. It contradicted the prevailing view. But Agassiz had evidence. He showed colleagues the polished bedrock, the parallel scratches, the U-shaped valleys carved by ice, the moraines, long ridges of debris left when glaciers retreated. You couldn't explain all of this with a flood. Slowly, scientists started to accept it. Charles Lyell, the most influential geologist of the era, was convinced by 1840. He saw the evidence in Scotland: scratched rocks, erratic boulders, glacial valleys. It all fit. By 1850, the Ice Age theory was mainstream. But scientists thought there had been only one ice age, one period when glaciers covered the northern continents. Then they melted. End of story. The next discovery changed everything. In the 1860s, geologists started finding multiple layers of glacial deposits. In some places, there were clear boundaries. Old glacial debris, then a layer of soil and plant remains, then more glacial debris, then another soil layer, then more ice deposits. Each layer represented a different climate. Glacial periods separated by warm periods. There hadn't been one ice age. There had been many. James Geekie, a Scottish geologist, documented this in detail. He identified at least 4 separate glacial periods in Scotland, each separated by warmer interglacial periods when plants grew and soils formed. The evidence kept mounting. In the Alps, geologists found the same pattern: multiple glacial advances, each one pushing rock and debris downhill, each retreat leaving behind distinct deposits. In North America, the evidence was even clearer. The Great Lakes region showed layer after layer of glacial till, different ice sheets at different times, some reaching as far south as Missouri, others stopping in Wisconsin or Minnesota. Consider what this means. The planet doesn't just freeze once and thaw, it freezes, thaws, freezes again, over and over, like a heartbeat, a slow, patient heartbeat that takes 100,000 years per cycle. But how could anyone prove this? How could you date rocks that were hundreds of thousands of years old? Radiocarbon dating wouldn't be invented until the 1940s, and it only worked on organic material less than 50,000 years old. The breakthrough came from an unexpected place: the ocean floor. In the 1950s, oceanographers started drilling cores from the deep sea, long cylinders of sediment pulled up from the bottom of the ocean. These cores contained the shells of tiny organisms called foraminifera, forams for short. Forams are single-celled creatures. They build shells from calcium carbonate. When they die, the shells sink to the ocean floor, layer after layer, year after year, for millions of years. Now, something interesting happens with these shells. They contain oxygen, specifically oxygen isotopes, oxygen-16 and oxygen-18. The ratio between these two isotopes depends on temperature. When the world is cold and ice sheets are growing more oxygen, 16 gets locked up in ice. That leaves more oxygen-18 in the ocean. Forams building shells during ice ages incorporate more oxygen-18. When the ice melts, the ratio shifts back. Scientists could measure these ratios. They could see the ice ages in the foram shells. Each layer of sediment represented a different time period. You could read climate history like a book. Cesare Emiliani did exactly this in 1955. He analyzed foram shells from Caribbean sediment cores. He found a clear pattern: warm periods and cold periods alternating over and over, going back hundreds of thousands of years. He identified what he called oxygen isotope stages, odd numbers for warm periods, even numbers for cold periods. Stage 1 is now our current warm period. Stage 2 was the last ice age. Stage 3 was a cooler period before that, and so on. The pattern was remarkable. The ice ages weren't random. They followed a rhythm, a cycle. roughly 100,000 years between major glacial periods with smaller variations in between. Other scientists confirmed this. They drilled cores from different oceans, the Atlantic, the Pacific, the Indian Ocean. Everywhere they looked, they found the same pattern, the same cycles, the same rhythm of ice ages. And here's what nobody expected. The ice didn't come back once or twice. It came back 8 times, 8 separate ice ages in the last 800,000 years, each one lasting about 90,000 years. Each warm period, like the one we're in now, lasting about 10 to 15,000 years. The planet spends most of its time frozen. The warm periods are brief interruptions, pleasant breaks between long icy epochs. Then came the ice cores. In the 1960s, scientists started drilling into the ice sheets of Greenland and Antarctica. These weren't like ocean cores. Ice cores contained actual ancient atmosphere. Tiny bubbles of air trapped when the snow fell and compressed into ice. You could measure the carbon dioxide in those bubbles. The methane, the temperature when the snow fell. You could see volcanic eruptions as layers of ash. You could count the annual layers like tree rings. The first deep ice core came from Camp Century in Greenland, drilled between 1963 and 1966. It reached bedrock at 4,600 feet. It contained ice over 100,000 years old. The data confirmed what the ocean cores showed. Regular cycles of warming and cooling, ice ages followed by warm periods, over and over. But the ice cores revealed something the ocean cores couldn't: the speed of change. Some transitions from ice age to warm period happened incredibly fast. Within decades, maybe even years, the climate could flip like a switch. Picture a scientist in Antarctica holding a cylinder of ice 2 inches across. The ice is clear in places, cloudy in others. Each cloudy band is a year of snowfall. Each clear section is summer melt that refroze. You can count them. 1 year, 10 years, 100 years, 1,000. And trapped in that ice in bubbles smaller than grains of sand is air from 50,000 years ago, 60,000, 70,000, air that mammoths breathed, air that Neanderthals breathed, air from a world completely different from ours. You measure the carbon dioxide, 200 parts per million during the Ice Age, 280 during warm periods. The difference is stark, consistent. Every time the planet warms, carbon dioxide rises. Every time it cools, carbon dioxide falls. In the 1990s, the Greenland Ice Core Project and the Greenland Ice Sheet Project, too, drilled even deeper cores. They found ice nearly 250,000 years old. The Antarctic cores went back further. The Vostok core, completed in 1998, reached ice 420,000 years old. Later cores from Dome Sea in Antarctica went back 800,000 years. 8 ice ages, 8 warm periods, all recorded in the ice. The pattern was undeniable. Scientists could now see the details. Each ice age wasn't uniform. There were cold periods and slightly less cold periods, advances and retreats. The climate wobbled even during glacial times. And the warm periods, the interglacials, weren't all the same either. Some were warmer than others. Some lasted longer. Our current warm period, the Holocene, has been remarkably stable, unusually stable compared to previous interglacials. The evidence was overwhelming. Ice ages happened. They happened regularly. They followed a pattern, and we were living in a warm period between them. But knowing that ice ages happened wasn't the same as knowing why. The discovery of the pattern just made the mystery deeper. What could cause such regular cycles? What force was powerful enough to freeze half the planet every 100,000 years? That question would take another set of discoveries to answer. And even then, the answer would be incomplete. Because the more scientists learned, the more complex the picture became. The ice ages weren't just about ice. They were about everything, the whole Earth system responding to some trigger, some combination of triggers, all working together in ways that scientists are still figuring out. It's kind of perfect, actually. Learning about ice ages while you're trying to sleep, these massive slow changes that happen over thousands of years. Nothing urgent, nothing that requires you to stay alert, just the Earth doing what it's always done. Freezing, thawing, freezing again, let the pattern carry you. The rhythm of it. 100,000 years is a long time to wait between ice ages. You've got nothing but time right now. Picture those 4M shells at the bottom of the ocean. Millions of them. Billions. Each one a tiny record of the water temperature when it formed. Each one settling gently to the seafloor, adding to the layers. Year after year, century after century, millennium after millennium, the ocean floor rises grain by grain, the shells pile up. And locked in their chemistry is a story. A story of ice and warmth, of slow cycles that stretch across epochs, of a planet that breathes in and out, freezing and thawing with a patience that makes human lifespans look like eye blinks. You might be wondering, if the pattern is so regular, why didn't anyone notice it earlier? Why did it take until the 1950s to figure out there were multiple ice ages? Part of the answer is technology. You need deep drilling equipment, mass spectrometers to measure isotopes, ships that can stay at sea for months drilling into the ocean floor. None of that existed in 1850 or 1900 or even 1930. But part of the answer is perspective. You need to think in deep time, to imagine scales that dwarf human experience. 100,000 years, 800,000 years, millions of years. Our brains aren't built for that. We think in days, seasons, years, maybe decades if we're trying hard. To understand ice ages, you have to let go of human timescales. You have to zoom out, way out, until countries disappear, until mountain ranges rise and erode, until continents drift, until ice sheets grow and shrink like slow-motion tides. The scientists who figured this out, they learned to think differently. They learned to read rocks like books, to see time in layers of mud, to understand that the scratch on a boulder tells a story millions of years old. Agassiz stood in the Alps and saw not just mountains, but time. Deep time, the marks of ancient ice, the evidence of worlds that came before. He looked at a valley and saw not just what it was, but what it had been, a river of ice, miles thick, moving with the patience of stone. That's the skill, learning to see through time, to look at the present and understand the past, to recognize that the world you're standing in is just one frame in a very, very long film. The ocean cores taught us this too. Each layer of sediment is a page in Earth's diary. You drill down, you pull up a cylinder of mud, you slice it thin, you look at it under a microscope, and there they are, the foram shells. Thousands of them in a single cubic inch. You measure their chemistry, you plot the ratios, and suddenly you're looking at a graph that shows 400,000 years of climate history. Ice age, warm period, ice age, warm period. The rhythm is clear, unmistakable. But something curious appears in that graph. The rhythm isn't perfect. The cycles are close to 100,000 years, but not exact. Sometimes 90,000, sometimes 110,000, sometimes 120,000. Why, if the cause is regular, shouldn't the effect be regular too? That's the question we're going to explore next. Because the answer to that question involves a Serbian engineer, calculations done in wartime captivity, and a discovery about Earth's orbit that changed everything. But before we get there, take a moment. Breathe, let this sink in. 8 ice ages in 800,000 years. 8 times ice-covered Canada. 8 times ice-covered Scandinavia. 8 times the sea level dropped 400 feet. 8 times everything changed. And 8 times the ice retreated. The planet warmed. Life came back. Forests spread. Animals migrated north. The cycle continued. We're living in the 9th warm period. The Holocene. It started 11,700 years ago. Every city you've ever seen. Every book ever written. Every piece of music. Every painting. Every scientific discovery. All of it happened during this warm period, before the Holocene humans existed. But we were nomads, hunters, gatherers, moving with the seasons, following herds. We didn't build cities. We didn't plant crops. We didn't have time. The climate was too unstable. Then the Holocene began. The climate stabilized, and suddenly we could stay in one place. We could plant seeds and know they'd grow. We could build structures that would last. We could accumulate knowledge across generations. Civilization is a child of the Holocene, born in this brief window of stability, this pause between ice ages. And now 11,700 years later, we're still here, still in the warm period. But for how much longer, that's a question we'll return to. But first, we need to understand why the ice comes and goes. What drives the cycle? What makes Earth freeze every 100,000 years? The answer is in the sky, in the way Earth moves through space, in wobbles so small you'd never notice them in a human lifetime. But given enough time, given tens of thousands of years, those wobbles add up to something massive. Ice ages, orbits aren't perfect circles. Earth doesn't glide around the sun like a ball on a string. It wobbles, it tilts, it shifts, and these tiny changes over thousands of years add up to something massive. Ice ages. A Serbian scientist figured this out in the early 20th century. His name was Milutin Milankovic. He was an engineer, a mathematician, a man who began his calculations before war came and continued them even when imprisoned. And he discovered something nobody else had seen. Earth's orbit changes, not randomly, in patterns, predictable cycles that repeat over and over. And when these cycles line up just right, the planet freezes. 3 cycles, 3 different wobbles, each one operating on its own schedule. The first cycle is about the shape of Earth's orbit. Right now, our path around the sun is almost circular. Almost, but not quite. It's slightly oval, stretched out. This shape changes over time, sometimes more circular, sometimes more stretched. The cycle takes about 100,000 years. When the orbit is more circular, Earth stays about the same distance from the sun all year. When it's more oval, we swing closer in summer and farther away in winter. The difference isn't huge, but it matters. The second cycle is the tilt of Earth's axis. Right now, our planet leans at 23.5 degrees, like a top spinning at an angle. This tilt gives us seasons. When the northern hemisphere tilts toward the sun, it's summer there. When it tilts away, winter. But that angle changes. Over 41,000 years, Earth's tilt shifts between 22.1 and 24.5 degrees. More tilt means more extreme seasons. Hot summers, cold winters. Less tilt means milder seasons. Cooler summers, warmer winters. And something matters here that might surprise you. It's not about how cold winter gets, it's about how cool summer stays. Ice builds up in winter. That's normal. But if summer isn't warm enough to melt, all the ice stays. Year after year, building, thickening, spreading. Less tilt means cooler summers, which means more ice survives, which means glaciers grow. The third cycle is the wobble of Earth's axis itself. Imagine a spinning top. As it slows down, it wobbles. Earth does the same thing. Our axis traces a slow circle in space. One complete wobble takes 26,000 years. This wobble changes which season happens when Earth is closest to the sun. Right now, we're closest in January. Northern Hemisphere winter. In 13,000 years, we'll be closest in July. Northern Hemisphere summer. This matters because it affects how extreme the seasons are. If you're closest to the sun during summer, that summer gets even hotter. If you're farthest away during winter, that winter gets even colder. 3 cycles, 3 wobbles, each one changing how much sunlight hits different parts of Earth at different times of year. Milankovitch calculated all of this, not with computers, with tables and charts and endless equations. He figured out exactly how much sunlight reached Earth at different latitudes during different seasons over the past 600,000 years. And he found a pattern. Every 100,000 years, the cycles lined up. The orbit became more oval, the tilt decreased. The wobble put the northern hemisphere farthest from the sun during summer. All at once, less sunlight in summer, cooler temperatures, ice that didn't melt. Glaciers that grew and grew and grew. Now imagine Milankovitch. Years before the Great War, he's a professor in Belgrade fascinated by climate. He starts working on these calculations in 1912. The math is brutal, page after page of trigonometry, orbital mechanics, solar geometry. Then war comes. August 1914. The Austro-Hungarian Empire declares war on Serbia. Milankovitch is visiting family in what becomes enemy territory. He's detained, held in Budapest for several months. But even in detention, his mind doesn't stop. He works on the calculations, without books, without tools, just his memory and whatever paper he can find. When he's finally released, he returns to Belgrade and continues the work. He publishes the first version in 1920. Then refines it in 1930, completes the full theory in 1941 with his magnum opus canon of insulation and the Ice Age problem. Nobody pays attention. The scientific community ignores him. His math is too complex. His ideas too different. He's from Serbia, not a major research center. And World War II is happening. Nobody has time for theories about ancient ice. Milankovitch dies in 1958, still mostly unknown. His work gathering dust. Then in the 1970s, something extraordinary happens. Scientists start drilling ice cores, long cylinders of ice pulled from Antarctica and Greenland. Ice that had been building up for hundreds of thousands of years, layer after layer, each one a snapshot of Earth's ancient atmosphere. They could measure everything: temperature, carbon dioxide levels, dust in the air, pollen from plants, volcanic ash, all preserved in the ice like a frozen library, and they found cycles. The ice showed clear patterns, warm periods, cold periods, repeating over and over. And when they measured the timing, it matched Milankovitch's predictions. Almost perfectly. 100,000 years between major ice ages. 41,000-year cycles in the tilt. 26,000-year wobbles in the axis, all there in the ice, undeniable. They also drilled cores from the ocean floor, sediment that had been building up for millions of years. Each layer contained tiny shells from plankton. These shells recorded the temperature of the water when the plankton lived. Warmer water, different chemistry in the shells. Colder water, different chemistry again. Same patterns, same cycles, same timing. Milankovitch was right. Nearly 20 years after his death, the evidence proved it. A scientist who died in obscurity had solved one of nature's greatest mysteries, but something strange appeared in the data. The orbital changes don't actually change the total amount of sunlight Earth receives. Not really. The planet gets about the same energy from the sun, whether the orbit is circular or oval, whether the tilt is steep or shallow. What changes is where that sunlight goes. And when. More sunlight at the equator, less at the poles, more in summer, less in winter. The total stays the same. But the distribution shifts, and that's enough. That tiny redistribution of sunlight is enough to trigger an ice age. Picture this. The difference in sunlight between an ice age and a warm period is only about 0.1%. A tenth of a percent, that's all it takes. Earth's climate is balanced on a knife edge. A tiny push one way starts the ice growing. A tiny push the other way melts it back. The orbital cycles provide those tiny pushes. Regular, predictable, inevitable. But there's something weird about the 100,000-year cycle. It's the strongest pattern in the ice core data, the most obvious rhythm. But it shouldn't be. The orbital eccentricity, the stretch of Earth's orbit, has the weakest effect on sunlight. Way weaker than the tilt cycle or the wobble cycle. Yet it dominates the ice age pattern. Scientists call this the 100,000-year problem. Why does the weakest cycle create the strongest effect? Nobody knows for sure. There are theories. Maybe the other cycles amplify it somehow. Maybe feedback loops kick in. Maybe ice sheets themselves create momentum that takes 100,000 years to build and break. Ice is heavy, really heavy. A mile-thick glacier weighs trillions of tons. That weight pushes down on Earth's crust. The land actually sinks under the ice. When the ice melts, the land slowly rises back up. But it takes thousands of years. Maybe that delay matters. Maybe the ice builds up over 90,000 years. Slowly, gradually, getting thicker and heavier. Then something tips it over the edge. The ice collapses. Not all at once, but fast compared to how long it took to build. Within 10,000 years, it's gone. Then the cycle starts again. The Milankovitch cycles are still happening. Right now, Earth is still wobbling, still tilting, still changing its orbit. The cycles never stop. Right now, we're in a warm period, an interglacial. The ice sheets have retreated to Greenland and Antarctica. Sea levels are high. The climate is relatively stable. But according to the cycles, we should be heading back toward cold. Slowly, over the next few thousand years, the wobbles should align again. Summer sunlight at high latitudes should decrease. Ice should start building up. Except it's not happening. Earth is warming. Fast. Faster than any natural cycle would predict. That's us. Human activity. Carbon dioxide from burning fossil fuels. Changing the atmosphere in ways that overwhelm the natural cycles. We've broken the pattern, for now. Whether that's good or bad depends on your perspective. Ice ages are hard to live through, but rapid warming creates its own problems. The Milankovitch cycles are still there, still operating, still wobbling Earth's orbit and tilt and axis. But we've added a new factor, a new force, and nobody knows exactly how it will play out. Will we delay the next ice age, cancel it entirely, or just postpone it until the carbon dioxide levels drop again? Thousands of years from now, the math that Milankovitch did in the early 20th century is still valid. The cycles are real, the patterns are clear. But we've added a variable he never considered. Human civilization, industrial emissions, the ability to change our own planet's climate. The wobbles continue, silent, slow, inevitable. Earth keeps tilting and spinning and circling the sun. The same cycles that have driven ice ages for millions of years. But now we're part of the equation too. And the next chapter of Earth's climate story is being written by both natural cycles and human choices. The ice remembers everything, every wobble, every tilt, every shift in Earth's orbit, trapped in those frozen layers, waiting to tell its story to anyone who drills deep enough to listen. So how do wobbles in space actually create ice on Earth? It seems impossible. Earth tilts a bit more, the orbit stretches slightly, and suddenly glaciers appear, miles thick, covering entire continents. The connection isn't obvious, but it's real, and it all comes down to summer, not winter. You'd think ice ages start because winters get colder. More snow falls. Temperatures drop. Ice builds up. But that's not how it works. Ice ages start because summers get cooler. Just a little bit cooler. Not enough to notice day to day, but enough that last winter's snow doesn't completely melt. Snow falls every winter in Canada, in Alaska, in Northern Europe. Feet of it. But every summer, most of it melts. The cycle resets. Winter adds snow. Summer removes it. Balance. But what if summer can't finish the job? What if the temperature stays just cool enough that some snow survives? Not all of it, just patches. In valleys, on north-facing slopes, places where the sun doesn't hit quite as hard. That leftover snow sits through the next winter. More snow falls on top. The old snow gets compressed, turns to ice, gets heavier, denser. Next summer comes, still a bit cooler than normal. More snow survives, more ice builds up. Year after year, decade after decade, century after century, the ice grows. At first it's just snowfields, then ice patches, then glaciers. Small ones in the mountains. But they keep growing, spreading, flowing downhill like frozen rivers. And something interesting happens. Ice changes everything around it. White surfaces reflect sunlight. Fresh snow reflects about 80% of the sun's energy back into space. Dark surfaces absorb it. Forests absorb about 90% of sunlight. Ocean water absorbs about 95%. So when ice covers the ground, less heat gets absorbed. The area stays cooler, which means more ice survives the next summer, which means more sunlight gets reflected, which means even cooler temperatures. It's a feedback loop. Ice creates conditions that make more ice. Scientists call this albedo feedback. Albedo just means reflectivity. High albedo equals more reflection. Low albedo equals more absorption. A forest-covered landscape has low albedo. Dark green trees soaking up sunlight. Warm ground. Snow melts quickly in spring. That same landscape covered in ice has high albedo. Bright white surface bouncing sunlight away. Cool ground. Snow barely melts at all. The Milankovitch cycles don't create much cooling on their own. The change in sunlight is tiny, less than 1%, but they trigger the feedback loop. And the feedback loop does the heavy lifting. It starts in the far north, northern Canada, Scandinavia, Siberia. These places are already cold, already get snow every winter. They're right on the edge, just barely melting all their snow each summer. When the orbital cycles reduce summer sunlight by even a tiny amount, these places tip over. Snow starts accumulating, ice begins growing, the ice spreads outward, south from the Arctic, down through Canada, across northern Europe, into Russia. Glaciers thousands of feet thick, moving, grinding, reshaping the land. And as the ice spreads, it reflects more sunlight, which cools more area, which allows more ice to form farther south. The feedback loop accelerates. But there's another feedback loop happening at the same time. In the ocean, cold water holds more dissolved gas than warm water. You can see this with soda. Cold soda has more fizz. Warm soda goes flat. Same principle with ocean water and carbon dioxide. As Earth cools, the ocean absorbs more carbon dioxide from the atmosphere. Less carbon dioxide in the air means less greenhouse effect. Less greenhouse effect means cooler temperatures, which means the ocean absorbs even more carbon dioxide. Another feedback loop, this one involving the whole planet's chemistry. Scientists can measure this in ice cores, tiny bubbles of ancient air trapped in Antarctic ice. Each bubble is a sample of Earth's atmosphere from thousands of years ago. During ice ages, carbon dioxide levels drop to about 180 parts per million. During warm periods, they rise to about 280 parts per million. The pattern is clear. Less carbon dioxide equals colder climate. More carbon dioxide equals warmer climate. The Milankovitch cycles start the process, but the feedback loops amplify it, turn a tiny change in sunlight into a massive change in climate. It takes time, though, a lot of time. The ice doesn't appear overnight. It builds gradually, over thousands of years. Each summer leaves a bit more snow. Each winter adds another layer. The ice sheet grows inch by inch, year by year. Imagine living through the start of an ice age. You wouldn't notice, not in your lifetime. Maybe summers feel slightly cooler. Maybe snow lingers a bit longer in the mountains. But nothing dramatic, nothing obvious. Your grandchildren might notice more. The snow line creeping lower, glaciers in the mountains getting bigger. Winters lasting longer. 1,000 years later, the changes are undeniable. Glaciers have advanced miles. Forests have retreated. The climate has shifted. 5,000 years later, ice covers half the continent. Everything has changed. The ice builds fastest at the beginning, when it's small and only in the mountains. Then it slows down as it gets bigger. Spreading across flatland takes longer. The ice has to flow, push outward under its own weight. At its peak, the ice sheets are 2 miles thick in places. The weight is incredible. So heavy it pushes Earth's crust down. The land actually sinks, hundreds of feet under the ice. All that ice has to come from somewhere. From the ocean. Water evaporates from the sea, falls as snow on the ice sheets, gets locked up in glaciers, doesn't return. Sea levels drop. During the last ice age, the ocean was 400 feet lower than today. Coastlines were completely different. Land bridges appeared. Britain connected to Europe, Alaska connected to Russia. You could walk between them. The ice keeps growing until something stops it, until the feedback loops reverse. And this is where it gets fascinating. The same orbital cycles that triggered the ice age eventually end it. Earth keeps wobbling. The tilt changes. The orbit shifts. After tens of thousands of years, the cycles swing the other way. Summer sunlight increases. Just a tiny bit, but enough. The ice starts melting at the edges. Slowly at first, just the southern margins. But melting creates its own feedback loop. As ice melts, it exposes dark ground underneath. Dark ground absorbs more sunlight, which creates more warming, which melts more ice. Remember the albedo feedback we talked about? It runs in reverse. Less ice means less reflection. More dark ground means more heat absorption. More heat means faster melting. The ocean warms up slightly, releases some of that dissolved carbon dioxide. More greenhouse gases in the atmosphere. More warming, more melting. The ice that took 90,000 years to build can collapse in 10,000 years, sometimes faster. The end of an ice age happens much quicker than the beginning, but something curious appears when you look closely at the timing. The orbital forcing the push from the Milankovitch cycles is the same strength going into an ice age as coming out of it. The change in sunlight is symmetrical, equal but opposite. So why does the ice grow slowly but melt fast? Nobody knows for sure. Maybe it's the feedback loops. Maybe they're stronger in one direction. Maybe ice is easier to melt than to build. Maybe there's some threshold effect, some tipping point where everything accelerates. Or maybe it's about where the ice is. Ice at high latitudes near the poles is stable, cold year-round, hard to melt. But as ice spreads south, it reaches areas that are warmer, more vulnerable. When the climate shifts, the southern ice melts fast. And once it starts, the feedback loops take over. The whole system is nonlinear. Small changes can have big effects. Thresholds matter. Timing matters. The way different cycles interact matters. This is why the 100,000-year cycle dominates, even though it has the weakest direct effect. It's not just about the sunlight. It's about how the system responds. How the feedback loops amplify the signal. How ice and ocean and atmosphere all interact. Earth's climate isn't a simple machine. It's not like turning a dial. It's more like a pinball game. You hit the ball and it bounces around, hitting different bumpers, changing direction, building momentum. Small differences in the initial hit create huge differences in where the ball ends up. The Milankovitch cycles are the initial hit. The feedback loops are the bumpers. And ice ages are the result of the ball bouncing around the system for 100,000 years. We can see this in the data. The ice cores show it clearly. Climate doesn't change smoothly. It jumps, sudden shifts, rapid transitions, then long periods of stability. The ice builds gradually, slowly, steadily, for 90,000 years. Then suddenly, within a few thousand years, it's gone. The climate flips, temperatures jump, sea levels rise, the world transforms. And then it stays warm for 10,000 or 15,000 years. An interglacial period, like the one we're in now. Stable, comfortable, easy to forget that ice ages are the normal state, because they are. For the past million years, Earth has been in an ice age about 90% of the time. The warm periods are brief interruptions, pleasant breaks between long frozen epochs. We live in one of those breaks. The Holocene, the current interglacial. It started 11,700 years ago when the last ice age ended, and according to the orbital cycles, it should be ending soon. Geologically speaking, the wobbles should be lining up to start the next ice age. Summer sunlight at high latitudes should be decreasing, snow should be accumulating, ice should be building. But it's not, because we've added something new to the system, something the Milankovitch cycles never accounted for. U.S. human civilization, industrial emissions, Carbon dioxide from burning coal and oil and gas. We've increased atmospheric carbon dioxide from 280 parts per million to over 420 in just 200 years. That's faster than any natural cycle, faster than the ocean can absorb it, faster than plants can use it. We've overwhelmed the system, and we've broken the pattern. The orbital cycles are still there, still operating. But we've added so much greenhouse gas that the cooling effect doesn't matter. Earth is warming instead. Fast. We've essentially canceled the next ice age. At least for now. At least for the next few thousand years. Maybe longer. Whether that's good or bad depends on your perspective. Ice ages are hard. Glaciers destroy everything in their path. Sea levels drop. Climate zones shift. Entire ecosystems collapse and rebuild. But rapid warming has its own problems. Different problems. Rising seas. Changing weather patterns. Species that can't adapt fast enough. The wobbles continue regardless. Silent, slow, patient. Earth keeps tilting and spinning. The cycles keep turning. The same forces that have driven climate for millions of years. But now there's a new force in the equation. Us. And nobody knows exactly how it will play out. How long our influence will last. What happens when the carbon dioxide levels eventually drop again thousands of years from now? The ice remembers every wobble, every tilt, every shift, recorded in frozen layers. A library of climate history stretching back 800,000 years. Maybe more. And it's still recording, still building, still waiting to tell its story to anyone who listens. There's a problem with the whole theory, a big problem. One that scientists noticed pretty quickly once they started looking at the actual data from ice cores and ocean sediments. The cycles don't match. Milankovitch proposed 3 cycles. The tilt cycle at 41,000 years, the wobble cycle at 23,000 years, and the orbital shape cycle at 100,000 years. But the orbital shape cycle is the weakest by far. It changes the amount of sunlight reaching Earth by only about 0.1%, barely anything. The tilt cycle is much stronger, changes sunlight by about 15%. The wobble cycle is moderate, changes it by maybe 5%. So logically, you'd expect the tilt cycle to dominate. The 41,000-year rhythm should be the strongest signal in Earth's climate records. And for a while it was. Go back far enough in the ice core data, before about 1 million years ago, and you see exactly what you'd expect. A strong 41,000-year pattern. Ice ages come and go every 41,000 years. The tilt cycle is in charge, but then something changes. Around 1 million years ago, maybe a bit earlier, the pattern shifts. The 41,000-year cycle fades into the background, and the 100,000-year cycle takes over, becomes dominant. It controls the rhythm of ice ages. This makes no sense. The weakest forcing somehow produces the strongest response. It's like tapping a wine glass gently with your finger and getting a huge ringing sound while hitting it hard with a spoon produces only a quiet clink. The system is responding backwards. Scientists call this the 100,000-year problem, or sometimes the Milankovitch problem, because it suggests something is wrong with the theory, or at least incomplete. The data is clear, undeniable. For the past 1 million years, ice ages have followed a 100,000-year cycle. Almost exactly. You can see it in ice cores from Antarctica, in ocean sediments from around the world, in cave formations, in ancient beaches. 8 ice ages in the past 800,000 years, each lasting about 90,000 years, separated by warm periods of 10 to 15,000 years. The pattern is too regular to be random, too consistent to be coincidence. Something is pacing it, something with a 100,000-year rhythm. But the orbital eccentricity cycle, the only natural cycle at that frequency, is too weak. The math doesn't work. The forcing is tiny. The response is massive. It's like pushing a child on a swing. A small push at the right time can build up a big swing. Resonance. Timing matters more than strength. But even resonance has limits. You can't push a swing with your pinky finger and expect it to go over the bar. There has to be enough force to work with. The eccentricity cycle barely changes anything. Earth's orbit goes from slightly elliptical to slightly less elliptical. The difference in sunlight is negligible. Less than the difference between a cloudy day and a clear day. Yet somehow this tiny change triggers massive ice sheets, miles thick, covering continents, lasting tens of thousands of years. Something else must be going on. Some amplification mechanism. Some way the system takes a weak signal and turns it into a strong response. Scientists have been arguing about this for decades, proposing theories, testing models, trying to solve the puzzle. One idea involves the ice sheets themselves. Maybe they have their own internal rhythm, their own natural cycle that happens to match the orbital cycle. Consider this. Ice sheets grow until they get too big, too unstable. Then they collapse. Not because of external forcing, but because of their own weight, their own dynamics. Maybe it takes about 100,000 years for an ice sheet to grow to the point where it becomes unstable, where the bottom starts melting from pressure and friction, where the whole thing begins to slide and break apart. The orbital cycles might just provide a nudge, a slight push that tips an already unstable system over the edge. The timing looks like it's controlled by the orbit, but really it's controlled by the ice. This theory has some support. Scientists know that ice sheets can collapse quickly, much faster than they grow. The end of the last ice age happened in just a few thousand years. Sudden, dramatic, like a switch flipping. But the theory has problems too. Why would the ice sheet cycle be exactly 100,000 years? That's a very specific number. And why would it sync up so perfectly with the orbital cycle? Coincidence seems unlikely. Another idea focuses on carbon dioxide. We know carbon dioxide levels drop during ice ages, from about 280 parts per million to about 180. That's a big change. And carbon dioxide is a powerful greenhouse gas. Maybe the carbon cycle has its own rhythm. Maybe the ocean absorbs and releases carbon dioxide on a 100,000-year cycle. And maybe this cycle somehow links to the orbital changes. But this just moves the problem. Why would the carbon cycle operate on a 100,000-year timescale? What drives it? The weak orbital forcing still has to do a lot of heavy lifting. Some scientists think multiple cycles interact. The 100,000-year cycle doesn't work alone. It combines with the 41,000-year cycle and the 23,000-year cycle. They beat against each other, create interference patterns, amplify certain frequencies, like musical notes. Play two notes close together and you hear beats, a pulsing rhythm. The combined sound is different from either note alone. Maybe Earth's climate responds to the combined signal of all three orbital cycles. And maybe the way they combine creates a strong 100,000-year beat, even though the individual 100,000-year cycle is weak. The math for this gets complicated. You have to model how different frequencies interact, how the climate system responds to multiple inputs at once, how feedback loops amplify some signals and dampen others. Computer models can do this, and some models do produce a strong 100,000-year signal from weak orbital forcing. But the models require careful tuning, specific assumptions about how ice sheets behave, how the ocean circulates, how carbon dioxide moves between atmosphere and ocean. Change the assumption slightly and the 100,000-year signal disappears, or becomes too strong, or shifts to a different frequency. This makes some scientists uncomfortable. If the theory only works with very specific assumptions, maybe it's not the right theory. Maybe we're missing something fundamental. There's another curious aspect to the 100,000-year cycle. It's not perfectly regular. Sometimes it's 80,000 years. Sometimes 120,000 years. The average is 100,000. But there's variation. If the orbital cycle was directly controlling ice ages, you'd expect perfect regularity. The orbital cycle is like clockwork, precise, predictable. It doesn't vary, but ice ages do vary. They skip beats sometimes, or double up. The rhythm has hiccups. This suggests the climate system has some independence, some internal variability. It's not just passively responding to orbital forcing. It's doing its own thing, and the orbital cycles influence it, pace it, but don't completely control it. Imagine a drummer keeping time. Most of the time they hit the beat exactly, but sometimes they're slightly early, sometimes slightly late. They add fills, change the rhythm. The underlying tempo is still there, but there's creativity, variation. Maybe Earth's climate is like that. The orbital cycles provide the tempo, but the climate system improvises around it. Or maybe the climate system is chaotic, in the mathematical sense, sensitive to tiny differences. Small changes in initial conditions create big differences in outcomes. Chaotic systems can look random, but actually be deterministic. Follow rules. But the rules are so sensitive that prediction becomes impossible. Like weather. We can forecast a few days ahead, but not weeks or months. The system is too chaotic. Maybe ice ages are chaotic too. The orbital cycles provide some structure, some predictability, but chaos adds noise, variation, makes each ice age slightly different. This would explain why the pattern isn't perfect, why ice ages sometimes come early or late, why the 100,000-year rhythm has wobbles, but it makes the problem harder to solve. Because chaos means we can't predict exactly. Can't say for certain what causes what. Can only talk about probabilities, tendencies, rough patterns. Some scientists think we're asking the wrong question. Maybe there isn't one cause, one mechanism, one explanation. Maybe ice ages result from multiple factors all working together, sometimes reinforcing each other, sometimes canceling out. The system is too complex for simple answers. The orbital cycles matter. The feedback loops matter. The ice sheet dynamics matter. The carbon cycle matters. Ocean circulation matters. Even random chance matters. All of these things interact, create a complex system, and the 100,000-year pattern emerges from that complexity. Not because of one dominant cause, but because of how everything fits together. This is unsatisfying in a way. Scientists like clean explanations, simple theories, elegant solutions. Complexity feels messy, hard to test, hard to prove. But maybe that's just how Earth works. Maybe climate is inherently complex. Multiple causes, multiple feedbacks, no single answer. The ice cores keep providing data, more detail, better resolution. Scientists can now see changes that happened over decades, sometimes years. The records are incredibly precise, and the more precise the data gets, the more complicated the picture becomes. There are cycles within cycles. Sudden jumps, gradual trends, regional differences, global patterns. Every answer raises new questions. Every solution reveals new problems. Why did the 100,000-year cycle start a million years ago? What changed before that? The 41,000-year cycle dominated. What flipped the switch? Now something interesting emerges from the data. Some scientists think ice sheets got bigger. Before a million years ago, ice ages were smaller. Ice didn't spread as far south, didn't get as thick, didn't last as long. Maybe once ice sheets reached a certain size, they started behaving differently, became more stable, harder to melt, took longer to build and collapse. And this changed the system's natural frequency from 41,000 years to 100,000 years. But why did ice sheets get bigger? What allowed them to grow larger than before? Maybe Earth cooled slightly, a long-term cooling trend over millions of years. As Earth cooled, ice could survive farther south, build thicker, last longer. Or maybe ocean circulation changed. The way currents move heat around the planet, a small change in circulation could allow ice to accumulate differently. Or maybe mountain ranges rose higher. The Himalayas, the Rockies. Higher mountains mean more area above the snow line, more places where ice can start growing. All of these things probably played a role, slowly, gradually, over millions of years, until the system crossed some threshold and the rhythm changed. We think we understand the pattern, then we look closer at this transition, this mid-Pleistocene transition scientists call it, and we realize the rules had changed. The system had shifted gears, started dancing to a different beat. The 100,000-year problem remains unsolved. Not because scientists aren't smart enough or don't have enough data, but because the system is genuinely complex. Multiple causes, multiple effects. No single explanation captures everything. And maybe that's okay. Maybe some questions don't have simple answers. Maybe the universe is messy, complicated, full of interactions we're still figuring out. The ice remembers it all, every cycle, every wobble, every shift, locked in frozen layers, waiting to tell its story. We can read that story now, extract the data, build the graphs, see the patterns. But understanding why the patterns exist, that's harder. That takes time, more research, more thinking. The 100,000-year problem isn't solved, but we're getting closer. Each study adds a piece. Each model refines our understanding. Each ice core reveals new details. And in the meantime, the cycles continue. Silent, patient, indifferent to our confusion. Earth keeps wobbling, keeps tilting, keeps moving through space. The ice keeps recording, keeps building, keeps waiting. So what does all this mean for our future? Let's zoom in on the time we're living in right now. The current interglacial. This is the warm stretch between ice ages. Scientists call it the Holocene. It started about 11,700 years ago. That might sound like a long time, but on the scale of Earth's history, it's just a blink. Picture this. If the whole history of the planet was a year, the Holocene would be a few seconds before midnight on December 31st. So what's special about the Holocene? Well, for one thing, it's when people built everything, cities, farms, writing, all of it. Before this time, life was wild and cold. Now the land is mostly green. The ice sheets are small, and the climate has been at least until recently remarkably steady. But how do we know how unusual the Holocene really is, and what makes this warm period different from all the other warm spells in the past? Let's dig into the evidence, layer by layer, and see what the planet has to say. First, let's start with the ice. Even though glaciers melted back at the end of the last ice age, a few giant ice sheets are still left, mostly in Greenland and Antarctica. But during the last glacial maximum, which was only about 20,000 years ago, things looked totally different. Huge sheets of ice covered Canada, Northern Europe, parts of Asia. If you lived back then, you would have seen walls of ice taller than skyscrapers, stretching for thousands of miles. As the world slowly warmed, the ice sheets shrank. Ocean levels started rising, swallowing up land bridges that once connected continents. That's why you can't walk from Siberia to Alaska now. But people could during the Ice Age. You can find old shorelines far inland where the sea used to reach. In some places, like Scandinavia, the land is still slowly rising, bouncing back from the weight of the old ice. Now let's look at the mud at the bottom of the sea. When you look at the layers from the Holocene, you see a huge change. The shells show that the ocean warmed up fast. The amount of carbon dioxide in the air jumped. The chemistry of the water changed. These shifts all line up with the melting of the ice and the start of the new warmer age. But something interesting appears when you look at all the interglacials. The Holocene isn't the only warm spell in the last million years. There have been at least 8 or 9 other interglacials since that big shift to 100,000-year cycles. Some were longer, some shorter, some were warmer, some cooler. But they all shared one thing: they were brief islands of warmth in a long sea of cold. Scientists figure this out by looking at ice cores from Antarctica and Greenland. Each layer of ice is a slice of old climate. By measuring bubbles of ancient air and looking at dust and chemistry, they can build a record that stretches back almost a million years. The pattern is clear. Every 100,000 years or so, the world warms up for a short time, usually about 10,000 to 15,000 years. Then, almost like clockwork, the ice returns. Let's talk numbers for a minute. During the coldest parts of the last ice age, average global temperatures were about 9 degrees Fahrenheit colder than today. That might not sound huge, but it's the difference between an ice-covered Canada and the forest we see now. Sea levels were about 400 feet lower. You could walk from what's now England to France. Mammoths and woolly rhinos roamed the plains. Then about 20,000 years ago, the world started to warm. By 14,000 years ago, the ice sheets were melting fast. Huge floods poured into the oceans. Sometimes lakes trapped by ice would burst, releasing more water all at once. The landscape changed quickly. Forests and grasslands spread north as the ice retreated. Animals followed. So did people. The start of the Holocene wasn't smooth. There were wild swings, like the Younger Dryas, a sharp cold snap that lasted about 1,200 years. Evidence for this comes from pollen in ancient lake mud and from tiny crystals in Greenland ice. Suddenly, right near the end of the Ice Age, temperatures dropped back down. Then just as fast, the cold ended and the world warmed again. Once the Holocene really began, things settled down. For the last 11,700 years, the climate has been unusually stable. Temperatures have gone up and down a little, but not by much. The pattern is almost flat compared to the wild swings before. Scientists even call this time the long summer. Why is this important? Because stability gave humans a chance to build. Before the Holocene, humans lived by hunting and gathering. They moved when the weather changed, following animals and wild plants. But once the climate steadied, people could start farming. They planted crops, raised animals, stayed in one place. Villages grew into towns, towns grew into cities, civilizations rose all over the world. So how do we know the Holocene was really stable? And not just in one place, but everywhere. The answer comes from dozens of clues. There are tree rings, which show how wet or dry each year was. There's pollen in lake mud, which tells us what kinds of plants were growing. There are cave formations, stalactites and stalagmites, which grow faster or slower depending on rainfall and temperature. All these records line up. The Holocene has been a time of calm, but it hasn't been completely flat. There were smaller wiggles in the climate. For example, about 8,200 years ago, there was a sudden cold snap that lasted for a century or two. Scientists think it was caused by a giant lake in North America draining into the Atlantic, changing ocean currents. There was also the so-called 4.2 kiloyear event, about 4,200 years ago. That was a drier, cooler period that hit ancient Egypt and Mesopotamia hard. Some kingdoms collapsed, others barely survived. Then there was the medieval warm period. About 1,000 years ago, when parts of Europe got warmer, Vikings sailed to Greenland and even North America. Later came the Little Ice Age, from around 1300 to 1850. Winters in Europe were colder, rivers froze, crops sometimes failed. But even these changes were small compared to the giant swings of the Ice Age. Let's pause for a second and look at what the evidence actually shows. In Greenland, ice cores, the layers from the Holocene, are thicker and more even. There are fewer big dust spikes. The amount of carbon dioxide in the air stays steady within a narrow range, about 260 to 280 parts per million, until very recently. Tree rings from all over the world show the same thing. Some years are better than others, but the pattern is gentle. No deep freezes, no wild heat spikes. This climate calm is a rare thing in Earth's story. If you look back over the last million years, most of the time was cold, dry, hard. Warm periods like the Holocene are short and precious. They're like breathing spaces between long, icy winters. Now let's talk about the animals and plants. During the Holocene, forest grew back where ice had scraped the land bare. Animals like deer, wolves, bison, they spread into new areas. Some big creatures from the Ice Age like mammoths and giant sloths didn't make it. They vanished as the climate warmed and people spread out. But many species found new homes. There's also a story in the mud at the bottom of lakes and oceans. Layers from the Holocene are full of pollen from trees and grasses. You can see forests marching north over thousands of years. In Europe, the forest came back first in the south, then spread north as it warmed. In North America, the same thing happened. Birch and pine gave way to oak and maple. Animals followed the trees. People did too. The story repeats in Asia, Africa, South America. Life changed with the land. But the Holocene isn't just a story of nature. It's the stage for human history. The first farms appeared in the Middle East about 10,000 years ago. Wheat, barley, lentils were planted. Sheep and goats were tamed. Soon rice farming began in China. Corn, beans, squash were raised in the Americas. All this happened during the Holocene. Without a stable climate, it probably wouldn't have been possible. You might be wondering about the numbers. The world's population before farming was small, maybe a few million people, scattered in tiny bands. By the time the first cities rose around 5,000 years ago, there were tens of millions. Today, there are over 8 billion. That's a huge change. And it all happened in this warm window. What about the world's ice? Greenland still holds a big ice sheet, but it's much smaller than during the Ice Age. Antarctica is even bigger, but it's far from most people. The last bits of ice in North America and Europe melted away about 8,000 to 6,000 years ago. Old shorelines, buried soils, ancient pollen, they all tell the story. Sea levels rose fast as the ice melted. In some places, the oceans swallowed up land that people once lived on. There are even underwater ruins off the coasts of India and the Mediterranean. People had to move as the seas came in. Let's not forget about climate surprises. Even in the Holocene, there were droughts and floods. Droughts hit North Africa about 5,000 years ago, turning green grasslands into the Sahara Desert. Evidence for this comes from ancient lake beds, buried sand dunes, even cave art showing animals that don't live there now. Other places got wetter for a while. The monsoon shifted in Asia, flooding some regions and drying out others. These changes show up in river mud, lake layers, even in the rise and fall of ancient kingdoms. But again, none of these shifts match the wild swings of the Ice Age. Now, what about carbon dioxide and greenhouse gases? For most of the Holocene, carbon dioxide stayed in a narrow band. That's what you see in ice cores. Only in the last 2 centuries has it shot up, mostly because of burning coal, oil, gas. This is a new thing, and scientists are watching closely to see what happens next. But let's stay with the past for a moment. The calm of the Holocene wasn't guaranteed. It was just good luck in a way. The planet's orbit, tilt, wobbles. They lined up to give us a break between ice ages. If you look at the timing, we're right about due for another cold period, at least by the old pattern, but something is different now. The amount of greenhouse gases in the air is higher than at any time in the last 800,000 years. The world is warming fast. This isn't what usually happens near the end of an interglacial. And here's what nobody expected. We might have broken the pattern, not the orbital cycles. Those keep running like clockwork. But the way the climate responds to them, we've added so much carbon dioxide that the next ice age might not come, at least not for tens of thousands of years, maybe longer. For most of the Holocene, life was shaped by gentle changes. Rivers shifted, forests grew and shrank, people learned to farm, animals found new places to live. You can see the traces of ancient farming in the soil. There are old fields in England, rice paddies in China, terraces in Peru. All these are marks of people using the calm weather to build something lasting. So what's the takeaway from all this? The Holocene is rare. It's a gift from the planet's strange heartbeat. A pause between long, freezing winters. It's been steady, but not perfectly calm. There have been bumps and chills, but compared to the wild rides before, it's been paradise. All the evidence lines up. Ice cores, mud, pollen, tree rings, lake layers, ancient shorelines. They all tell the same story. A long, warm window, just right for humans to settle down and build. Will it last? That's the big question. If the pattern of the last million years holds, another ice age should be coming someday. But with the new spike in greenhouse gases, the future is wide open. The story of the Holocene is really the story of us. We're here because the world got lucky, if you know where to look. In the quiet layers of mud, in frozen air bubbles, in the rings of old trees, in the seeds of ancient farms. It's strange to realize how much depends on a planet's rhythm. One long summer, and here we are. Cities, science, art, all of it. The calm between the storms. So when you look at a map or watch the seasons change, keep this in mind. This isn't normal for Earth. It's special. And it won't last forever. But for now, we're still here, still in the warm period. And that rhythm, that slow, patient heartbeat of ice and warmth, it continues. Silent, deep, waiting. You are sitting here, listening to me talk, in a moment between two ice ages. Your ancestors fought through those dark winters, not knowing if spring would come. But they survived. They loved. They had children. And a small part of them, DNA memories encoded in genes, lives in you. You are the product of 800,000 years of persistence. Picture that as you drift off. The ice remembers everything, every wobble, every tilt, every shift in Earth's orbit, trapped in those frozen layers, waiting to tell its story to anyone who drills deep enough to listen. We've walked through 800,000 years together, 8 ice ages, 8 warm periods, and now we know. Not everything, but enough. Enough to see the pattern, enough to understand the rhythm. The cycles are real. The wobbles matter. The ice amplifies. The ocean remembers. The carbon shifts, and through it all, the planet breathes. In and out, cold and warm, with a patience that makes our lives look like fireflies on a summer night. What can we do with this knowledge? We can understand our place in deep time. We can recognize that change is the only constant. We can appreciate that we're living in a rare moment, a brief window of stability. We can make choices about how we treat this planet, about what we leave for future generations, about whether we work with Earth's rhythms or against them. The ice ages teach us patience. They teach us that small changes, given enough time, become massive transformations. They teach us that feedback loops matter, that systems are complex, that we're part of something much bigger than ourselves. Rest easy. You're part of something much bigger, much older, much more beautiful than you can imagine. The ice will come again. Or maybe it won't. We've added our own chapter to this ancient story, and how that chapter ends is still being written. But the story goes on, the wobbles continue, the cycles turn, and you, for this moment, are right in the middle of it. Good night, and keep this with you. You're living in the long summer. Every day you wake up in this rare window of warmth and stability is a gift from 800,000 years of planetary breathing. Enjoy it, cherish it, and maybe, just maybe, help it last a little longer. The ice clock keeps ticking, silent, patient, eternal. And now you know how to read it.